Sir Joseph John Thomson, more commonly known as J.J. Thomson, was born on the 18th of December 1856 in Manchester, England. Demonstrating outstanding ability in mathematics and science since he was a child, he was accepted into Owens College at the very young age of 14. 6 years later, in 1876, he began studying at Trinity College, Cambridge, after his mathematics professor recognised his talent and urged him to apply for a scholarship there. In 1880, Thomson received his Bachelor of Arts degree in mathematics. He was second wrangler, meaning he was the second highest scoring student. In 1881, he obtained his Master of Arts degree in mathematics. Thomson began his career in 1884 when he was appointed Cavendish Professor of Physics at the University of Cambridge, a surprising success considering the many other candidates that possessed far more experience in laboratory work, whereas Thomson was known for his work in mathematics. He was awarded a Nobel Prize in 1906 and knighted in 1908. He passed away on the 30th of August 1940 and was laid to rest in Westminster Abbey alongside Isaac Newton and Ernest Rutherford.
J.J. Thomson's contribution to many fields of science and the mathematical analysis of our world was epitomised by his use of the Crookes tube. Unlike many of his contemporaries, who were also using the apparatus, Thomson utilised a superior vacuum technique to effectively remove all of the air from the tube, minimising any ionisation of air particles and the misdirection that would induce. He fired a cathode ray through an anode collimator to focus the ray into a fine beam that was projected to the end of the tube. By placing a coil around it, he then exerted a magnetic force on the beam, which resulted in a centripetal force. This was equated to a magnetic field force, which was produced onto the beam. By balancing these, the beam was returned to its original position. Therefore, by equating the magnetic and centripetal force, he could now also equate that with an electric force. He could thereby rearrange the equation to find the charge-to-mass ratio algebraically. By substituting in known variables that he could measure from his experiments, he could find a numerical value for the charge-to-mass ratio of what is now known as an electron. His use of algebraic manipulation to find this ratio was then expanded on later by Millikan and Fletcher in their oil drop experiment. By atomizing oil drops and spraying them into the apparatus they built, they could find the terminal velocity of the drops, define the force due to gravity, and then equate them to an electric field similarly to Thomson. However, as now more variables were controlled and known to the scientists, they could determine the actual charge on one electron, very closely to the accepted value today, thereby showing Thomson's effect on the future of not only mathematical descriptions of physical events, but the whole direction of scientific discourse at the time.
In 1904, J.J. Thomson proposed the first ever scientific model of the atom, a proposition which came very shortly after the discovery of the electron. His plum pudding model consisted of many small negatively charged plums mixed into a larger positively charged pudding. While it was later discovered to be wrong, this model inspired many, including his own student at the time, Ernest Rutherford, who went on to propose the planetary model of the atom, a much more accurate representation of what we now know to be true. So how did J.J. Thomson affect modern mathematics as we know it today? His discovery of the charge-to-mass ratio was a groundbreaker in paving the pathway for modern physics. More specifically, without the work of J.J. Thomson, we would not be able to complete the mathematical problems we are faced with surrounding electrons, and hence hindering our understanding of different elements and their individual behaviours.